let's start with something simple, namely the Markov assumption. So remember, in the Markov assumption, the idea was that we have that, x hat of t is some function of, xt minus tau up to xt minus 1. And you could then just go and, train a regression model, use it to predict the next step, and you iterate. Okay? So let's see how that works in practice. Okay, so let's see. I'm going to generate some data. Let me just quickly run this. So I'm doing my usual import ritual, right? This is just to make sure everything displays nicely. I'm going to pick a 4-dimensional embedding, so tau equals 4, so I'm going to look at the 4 previous observations. I'm going to generate 1,000 points in total, nicely evenly spaced. And the data is going to be utterly boring, namely it's just going to be a sine curve plus some noise added. Okay? So it's, pretty boring. Let's actually see what this looks like, because that's a lot easier to grok rather than just, looking at the code. Well, it's a sine curve. It's a very noisy sine. Right? So, okay, nothing special. You could easily assume that you can, regress on that. It's not that easy because there's a lot of noise added to it, right? So if you only have 4 adjacent points, you may not be able to predict quite that well. But okay, anyway, let's see. So the first thing I need to do is I need to actually generate the data set and, well, define a model. So I'm going to first generate a data set. So I'm going to use, well, if I have embedding of 4 and I have, 1,000 observations, then, since I have now vectors of, the length 5, so I basically need to make a smaller object, right? T minus embedding, and then also embedding dimension, right? Because I have, 4 dimensions times, that length. And then what I do is I just now assign the values into this feature vector. And the only slightly more convenient thing that I'm doing is I'm not assigning it, one time step at a time. But if you think about it, right, so here's my vector. This is embedding dimension 1, 2, 3, 4. I'm going to take this vector here, and I'm going to shift it by 1. I'm going to shift it by 2. Shift. One more. Right, oops. Okay. I'll shift it by, 1, 2, 3, 4. And in doing so, of course, any slice that I pick out here has exactly the data, in the time series shifted by 1 step each relative to each other in that vector. That's just a lot faster because now my for loop goes over 4 entries as opposed to over 1,000. Not that it matters because the data set is tiny, but still. Okay, and labels are just, that embedding. Right. Now, the training data set is the first 600 observations. And so now I have a training data set and a test data set, so I perform exactly the operations that you would. I just, call the gluon data set constructor and call it an array data set. Right. And I picked, the first and train observations for training, and I'm going to pick the rest for testing. Okay. And then, okay, I'm going to define a very boring deep network. I'm going to start with, whatever input dimensions I have, and map into 10 hidden dimensions, another layer of 10 hiddens with a ReLU, then output 1 because we're going to do regression, and I pick Xavier initialization. So this is about as boring as you could imagine, the last thing I need to do is I need to define a loss, so I'll just pick the L2 loss. This is essentially state of the art, the first lecture when we introduced multi-layer perceptrons. None of this should be even in the remotest surprising to you. Any questions so far? Okay. Everybody cool with it? Good. So, okay, here's the trainer. Again, very straightforward. Mini batch size of 16. Why 16? Because it's a nice number. It's 2 to the 4. Could have picked 32 if I'd wanted to, right? I take, a trainer. Just I pick Adam here. Why? Because Adam kind of works. Could have probably picked 5 other solvers and it wouldn't have mattered, but I need to pick a solver. I pick my iterator on the training data, and then I just perform training where I go over the data epochs many times, and I just pick the XY pairs from the data iterator. Compute, turn on autograd, compute the loss, compute the gradient of that, and I perform the update. And in the end, I go and compute the loss, right, after the end of every epoch, and I print that loss. Right, L.mean, that gives me the average loss, and as numpy such that I can print it. In the end, when I'm done, I return the network. Okay. Is there anything that you want me to cover again about this? Okay. Don't be shy. Okay, good. Well, then let's train it, right? We can do that. That was quick. And it works fairly well, and we get like, 2.8% error, right? That's okay. Well, it's a regression problem. So that's the regression loss. And yeah, that's it. And basically, I could have stopped after 4 iterations or whatever. It doesn't matter. Okay, so now comes the moment of truth. Let's actually see how this behaves. Okay. So the blue curve is, the data, and the orange curve is the estimate. I think that works pretty well, right? Right, so that looks like we just solved the problem, right? Perfect error, right? And it nicely reconstructs things. And so now we can all go home. Okay, can somebody see something that wasn't so bright about what I just did? There is something really wrong with this curve, or with this approach rather. Any ideas of what's really stupid here? Okay?
I'm just confused by one point, because for a task data set, it's like for training, if I understand correctly, we're just like shifting so we go like one by one at a time. Right? For a task set, do we still have the true answer? Because it's just like adding 1 at the end.
Okay, so the question is what happens at test time? So do we have the correct data? You're on absolutely the right track. So the question was, at test time, do we have, the past tau observations, right? And the answer is no, obviously we don't, right? So you're spot on. This is exactly the issue. We right now pretended that at test time we still have those past observations, and then we just want to predict for the next day. So if that were the task, we would do exceedingly well. So what are we supposed to do then? Any suggestions? What could you do?
Use a prediction.
You could basically take one observation, predict, for the first unknown day, and then use that prediction of what I have so far plus the first unknown day to predict the second unknown day and then the third and keep on going, right? Okay, let's see how that goes. This is exactly what I'm doing here. So predictions, right? So for the first, few steps, we have the same thing. And then you go and essentially prediction at step I, you could take the network of the predictions that I have used so far and fill that in. Okay. Let's see how that goes, right? That's basically all this code does. And it goes spectacularly wrong. So the green curve are the predictions, and basically what I've done is after, step 600, where we no longer have any data, which is around here, I just kept on letting it predict forward. And you can see basically it just very quickly converges to the constant function and it stops doing anything meaningful. In other words, this model is exceedingly dumb, right? So in other words, if I want to predict forward by more than one step with that autoregressive model, often things go badly wrong. Okay, so you might wonder, well, okay, that's kind of obvious. Everybody knows that. Well, actually, if you talk to customers, you talk to them about time series forecasting, sometimes you need to point that out. Right? As in, it's very, very easy to get trapped by this yourself. So make sure that if you're dealing with time series data and you want to forecast, over an entire sequence, did you actually go and do that? Okay. It's a mistake that's very, very easy to make. Okay, so let's see how well this actually works. So what I did here is I basically ran the same thing as before, just that I looked at 4, 8, 16, and 32 steps. And this graph here shows what happens if I have the 4-step, 8-step, 16, and 32-step prediction error. And you can see the model kind of still works at 4 to 8 steps, and it falls down at 16, and at 32 it's pretty useless. Right. So in other words, this model is quite useful for very short-term forecasts, but for long-term forecasts, I would not want to put any money into it. Okay. So this is the story of autoregressive models. Any questions so far? Right. Okay, good. Then